In this example for 13.8, we want to find the relative extrema for f of xy equals 2xy minus 1/2 the quantity of x to the fourth plus y to the fourth, and then plus 1. It may be easier for this one when you're finding the critical points to distribute that negative 1/2 before taking the derivative. So we can rewrite our function f of xy as 2xy minus 1/2 of x to the fourth minus another 1/2 of y to the fourth plus 1. To find the critical points, we want to find where the partial with respect to x and y are both 0 at the same time. So we take the partial with respect to x. We treat x as a variable and y as a constant. That derivative is 2y minus 2x to the third. We also want to take the partial derivative with respect to y, and that partial derivative is treating y as a variable and x as a constant to get 2x minus 2y to the third. We want to find out where those are both equal to 0 at the same time. Now here we have a system of equations. We cannot use a matrix for this one because they are not linear equations. We can do some substitutions though. In the first equation, you can solve for y. If you solve this for y, you get y is equal to x to the third. If you add x cubed to both sides and then divide by 2, we get y equals x to the third power. Now we're going to take that y in the first equation, what y equals in the first equation, and plug it into or substitute into the second equation. And when we do that, we get 2x minus 2, replacing the y with x to the third equals 0. And by simplifying this, we get 2x minus power to a power. We multiply those powers together to get 2x to the 9th equals 0. We can solve this polynomial equation by factoring out a 2x, and you get 1 minus x to the 8th equals 0. You can set each factor equal to 0. When you set 2x equal to 0, you get x equals 0. That's going to be one of our critical points. If you set 1 minus x to the 8th equals 0, you get 1 is equal to x to the 8th. And this actually has two solutions. One where x is equal to positive 1 and one where x is equal to negative 1. Now these are the x values for our critical points. We want to put all these back into here to find our y values. So when x is equal to 0, we get y is equal to 0. When x is equal to positive 1, y is equal to positive 1. And when x is equal to negative 1, y is equal to negative 1. So we have 3 critical points. For each of these, we have 1 point, 2 points, 3 critical points. We're going to use the second partials test 3 times to determine what type of relative extrema we have. Now in order to do the second partials, we also need to find the higher order partial derivatives. We want to find the partial derivative with respect to x and x again. Okay, go back to the first partial with respect to x and take the derivative of that, and you're going to get negative 6x squared. Take the partial with respect to y and y again. Treat y as a variable and we get negative 6y squared. And find the mixed partial fxy. That mixed partial is going to be 2. Now our d value. The d in the second partials test is fxx evaluated at the critical points a, b, fyy evaluated at the critical points a, b, minus the mixed partial evaluated at the critical point that quantity squared. All right, so if we take a look at the first point at 0, 0, at 0, comma 0, the value for D is equal to the second partial with respect to x evaluated at 0, 0. Plug in 0 here, we're going to get 0, times the partial with respect to y, plug in the 0 here for y to get 0, minus the mixed partial, which is 2, quantity squared, and that gives us a negative 4. That's at the critical point 0, 0. At the next critical value, where x is 1 and y is 1, the value for D, plug 1 here for x into the second partial with respect to x, and that's negative 6. Plug in 1 for y times negative 6 minus 2 squared, and that is equal to 32. And then at the last critical point, negative 1, negative 1, the value for D, plug in negative 1 for x and y, it's negative 6 times negative 6 minus that 2 squared. Again, you get 32. Now, using the second partials test, and if we go back to this slide here, we're looking at when D is positive or negative. If D is negative, we have a saddle point. If D is positive and the second partial is positive, then it's a relative min. If D is positive and the second partial is negative, then we have a relative maximum. It looks like for the first one, when the D was negative, we have a saddle point. And for the second and third critical points, the D was positive, but the second partial was negative. So we have 2 relative maximums and 1 saddle point. So in this case, this right here, when the D is negative, we have a saddle point. And in both of these, where the D is positive, but these are negative, we have relative max. So our final points, our saddle point is when x is 0, y is 0, and then if you plug in 0 and 0 into both of those for the original equation, you can get the z value. That's the point in space. And then for the relative maxes, the points 1, comma 1, comma, if you plug that in and simplify, you get the z value. And for negative 1, negative 1, 2, you've got your 3 points. You've got 1 saddle point and 2 relative maximums. Now this is a problem that is from the textbook. In fact, if you look at number 26 from section 13.8, you can see a picture of this, and it's nice to be able to look at the picture and just verify that we have a saddle point and 2 maximums. Now this is the picture. You can see in the middle right there at the point 0, 0, 1, it does look like a saddle, and it looks like we have 2 high points there. Those are relative maximums. Here we can just rotate so you can see from different perspectives the saddle point. You see the parabola opening up one way and then opening down the other way. That's your saddle point, and those 2 high points are your relative maximums.